PT Multibangun Rekatama Patria adalah perusahaan nasional yang bergerak di bidang industri geosintetik. Sejak didirikan pada tahun 1998, perusahaan ini telah menangani ratusan proyek yang tersebar di seluruh Indonesia. Dengan pengalaman yang dimiliki, menjadikan PT Multibangun Rekatama Patria dipercaya menangani proyek-proyek dari perusahaan multinasional milik pemerintah dan swasta. PT Multibangun Rekatama Patria selalu menjaga kualitas material dan pekerjaan dengan didukung oleh tim yang kompeten dan berpengalaman di bidangnya. Visi PT Multibangun Rekatama Patria adalah menjadi pemimpin pasar dalam industri geosintetik di Indonesia yang selalu bersaing dengan sehat. Misi PT Multibangun Rekatama Patria adalah menjalankan kegiatan perusahaan dengan standar etika yang tinggi dan bermartabat disertai dengan kejujuran dan integritas. Meningkatkan kesadaran pengguna produk geosintetik untuk memilih produk dan solusi yang tepat atas masalah proyek yang dihadapi. Menjual dan melakukan pemasangan produk-produk geosintetik yang berorientasi pada kepuasan pelanggan dengan memberikan pelayanan berupa material berkualitas dan jasa pemasangan oleh tenaga-tenaga ahli dan berpengalaman. Mengembangkan perusahaan dengan sumber daya yang modern dan profesional. Memberikan penghargaan kepada karyawan melalui kesejahteraan yang baik, penyediaan lingkungan kerja yang aman dan nyaman, serta kesempatan untuk mengembangkan karir. Produk-produk PT Multibangun Rekatama Patria. Produk Tensar System terdiri dari Geogrid Tri-X, terbuat dari bahan polipropilin berkualitas yang berfungsi sebagai stabilitas tanah dasar, khususnya pada tanah lunak. Multi-block retaining wall system. Multi-block retaining wall system merupakan sistem konstruksi dinding penahan tanah segmental, perpaduan antara modular blok beton sebagai facing dan tensar uniaxial geogrid sebagai perkuatan tanah. Geomembran. Geomembran terbuat dari polimer plastik yang bersifat kedap terhadap cairan. Kami juga menyediakan produk-produk geosintetik lainnya seperti geotekstil, material drainase, serta geosintetik clay liner yang menjadi solusi bagi proyek-proyek Anda. Gudang PT Multibangun Rekatama Patria hanya 5 menit dari gerbang tol Bitung Tangerang, sehingga memudahkan akses pengiriman material. Gudang PT Multibangun Rekatama Patria terletak di kawasan pergudangan pengembangan kawasan terpadu 2, Bitung Tangerang. Yang mempunyai luas 3.300 meter persegi yang dapat menampung material geosintetik dengan pengaturan dan penyusunan material yang tertata rapi. serta pengoperasian alat dengan tenaga profesional. Kami pastikan material geosintetik tetap terjaga kualitasnya hingga sampai di lokasi proyek. Selalu ready stock dan pelayanan profesional adalah komitmen kami. Dengan pengalaman dan pelayanan yang teruji, maka jangan ragu untuk menghubungi kami. Kunjungi website kami di www.multibangunpatria.com.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi kepada Bapak, Ibu, dan rekan-rekan mahasiswa sekalian. Saya ucapkan selamat datang di acara MRP Webinar Series yang pertama. Pada hari ini bertemakan An Introduction to Soil Behavior and Index Properties pada pagi hari ini, tanggal 17 Februari 2021. Webinar ini dipersembahkan oleh PT Multibangun Rekatama Patria, Geosintetik Spesialis. Sebelum memulai acara, perkenankanlah saya membacakan susunan webinar kali ini. Pertama, akan dibacakan tata tertib dan tata cara dalam webinar kami. Yang kedua, sambutan dari Bapak Insinyur Isparmo IPM selaku perwakilan dari PT Multibangun Rekatama Patria. Acara kemudian dilanjutkan dengan paparan oleh Bapak Michael Dobie, dilanjutkan dengan sesi tanya-jawab. Sebelum mengakhiri acara, kami juga menyiapkan kuis berhadiah sebesar Rp150.000 per peserta untuk 3 orang pemenang. Maka dari itu, peserta dimohon untuk tidak langsung meninggalkan webinar setelah paparan berakhir. Informasi terkait sertifikat dan lainnya akan diumumkan di akhir acara. Demi kenyamanan bersama, saya akan bacakan terlebih dahulu tata tertib webinar pagi hari ini. Presentasi oleh pembicara akan dibawakan dalam bahasa Inggris. Apabila Anda memiliki pertanyaan untuk pembicara, dapat langsung diketikkan dari sekarang dan selama presentasi berlangsung melalui fitur Q&A yang terletak di bagian bawah layar Anda. Pertanyaan bisa dapat disampaikan dalam bahasa Indonesia maupun bahasa Inggris. Webinar kali ini juga disiarkan secara langsung di channel YouTube kami, yaitu di Multibangun Rekatama Patria atau di link s.id/webinar MRP Live 1 atau yang kami share pada kolom chat. Untuk mempersingkat waktu, saya persilahkan Bapak Insinyur Isparmo IPM selaku perwakilan dari PT Multibangun Rekatama Patria. Untuk memberikan sambutan kepada Bapak Isparmo, saya persilahkan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak dan Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi Bapak, Ibu, dan saudara-saudara sekalian. Perkenalkan, saya Isparmo, mewakili PT Multibangun Rekatama Patria, perusahaan geosintetik spesialis yang sudah berpengalaman melakukan suplai dan mengerjakan proyek geosintetik sejak awal tahun 90-an. Kami melakukan penjualan dan pemasangan material geosintetik seperti Tensar geogrid, di sana ada uniaxial geogrid, triaxial geogrid, dan biaxial geogrid. Kemudian multi-block retaining wall system, perkuatan timbunan atau lereng menggunakan sistem Tensar wrap-round atau Tensar geogrid. Kemudian geomembran, geotextile, dan material drainase seperti zip drain dan strip drain. Kami berencana untuk secara rutin berbagi pengalaman kami berkaitan dengan geosintetik dan geoteknik melalui webinar Zoom ini. Sharing webinar ini kami adakan sebagai bentuk kontribusi kami di dunia keteknik sipilan secara umum dan geoteknik pada khususnya. Semoga bisa memberikan manfaat yang positif. Sebagai penutup, jangan lupa protokol kesehatan 3M, memakai masker, mencuci sabun, dan tetap menjaga jarak sebagai antisipasi dari penularan virus COVID-19. Dan jangan lupa tetap olahraga teratur. Demikian yang bisa kami sampaikan. Terima kasih. Selamat mengikuti webinar. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak Isparmo atas sambutannya. Selanjutnya, webinar pada hari ini akan bertemakan Soil Behavior and Index Properties yang akan dibawakan oleh Bapak Michael Dobie yang merupakan Regional Manager Asia Pacific of Tensar. Sebelum beralih ke Bapak Michael Dobie, saya akan membacakan CV beliau. Bapak Michael Dobie telah menempuh kualifikasi akademiknya pada tahun 1973 di University of Bristol dengan gelar sarjana Bachelor of Science Civil Engineering dan melanjutkan di Imperial College London pada tahun 1977 dan berhasil meraih gelar Master of Science in Soil Mechanics under Professor Bishop. Beliau mendapatkan gelar profesional Chartered Engineering di UK pada tahun 1978 dan merupakan seorang fellow ICE di tahun 2011. Beliau juga mendapatkan Chartered Institution of Highway and Transportation pada tahun 1992. Bapak Michael Dobie memiliki pengalaman lebih dari 40 tahun di bidang geotechnical engineering di Inggris maupun di luar negeri, terutama yang berhubungan dengan jalan raya, perumahan, jembatan, dan dermaga. Baiklah, sekali lagi saya ingatkan kepada Bapak dan Ibu yang memiliki pertanyaan, untuk Bapak Michael Dobie bisa langsung menggunakan fitur Q&A yang terletak di bagian layar Zoom Anda. Pertanyaan dapat disampaikan dalam bahasa Indonesia maupun bahasa Inggris. Tanpa memperpanjang waktu, kepada Bapak Michael Dobie, saya persilakan.
Good morning, everybody. I hope you can hear me and that you can see the first slide of my presentation. I'd like to welcome you also to this series of webinars organized by Multibangun Rekatama Patria. And I have the great pleasure to conduct these webinars. And this first one is going to be an introduction to soil behavior and index properties. So it's the first in a series. So in this particular webinar, we're going to look at soils, their origins, and some of the basic index tests that we use to classify them. And this, of course, is going to help us to understand their basic properties and behavior as engineering materials, in particular as fills. We work in an area of reinforced soil structures, so we're always interested in the properties of the fill materials that we use. And there will be later webinars looking at other aspects of the engineering and mechanical behavior of soils as well. This is an outline of the webinars we plan. We're currently February, and that's the one today. And then I have some further titles there. That might change slightly as we go through these, but we will mention the second one a little bit later on when we finish this first webinar. So soils. Soils are incredibly varied materials. So we see some interesting pictures here. A sand dune, an expansive soil, peat, a river gravel, you can see rounded, and a microscopic view of clay minerals. I think what you can see from those 5 pictures is that soils are very varied. So understanding their properties and using them as engineering materials requires that we do have a very good level of understanding of how these materials work. I'm just going to put a timer on so that I know where we have got to. So who should be listening to this webinar? Well, first of all, I should say I'm not trying to teach soil mechanics. What I'm trying to do is to just provide some basic information, and I want to illustrate it with examples from real soils and real experience. If you like, it's some of the lessons that I've learned over many years, which I think are important. There'll be a mixture of some simple explanations and also some more advanced concepts. Please look out for these little blue boxes. The idea of these blue boxes like this is that they will either add some extra information or maybe pose a question, and maybe that question could be part of the quiz later on. And this is aimed at civil engineers who have involvement in ground engineering, which, to be honest, should be most civil engineers. It might be useful or interesting to more experienced geotechnical engineers. And although I'm really concentrating on fills, especially fills to be used for reinforced soil, there's a lot of general geotechnical information presented as well. Some suggested reading. Well, in Indonesia, we're very lucky. There are 2 extremely good books which appear to have much the same title, both written by Dr. Laurie Wesley, who is a name that is well known here. The left-hand one is a fairly simple book, but the other one is rather more complex, goes into much more detail on the topic of soil mechanics, in this case for both alluvial and residual soils. Just so you can see what they look like, there is the simpler book. You can often find this available in the bookshops here. I tend to buy them when I see them because they're really inexpensive, and probably in some later webinars we may well be offering some of these as prizes to the questions that we might pose to you. If you want something to go a bit further or something different, the well-known book by Bowles, I'm pretty sure that has been translated into Bahasa Indonesia in the past. But one book that I rediscovered recently was a very famous text, the Soil Mechanics and Engineering Practice by Tensar and Peck, but it's been updated in a 3rd edition by Professor Mesri. And I'd have to say, there's a lot of very interesting and excellent information in that book, if you're interested to find a text to study this subject in more detail. So the content today is something like this. There'll be an introduction. We'll look briefly at the origin of soils. We'll talk about things like stress history and earth pressure at rest. Then we'll talk about obtaining geotechnical data. After that, the composition, classification, and naming of soils. Then these important properties for clays, the Atterberg limits. We'll talk briefly about soil phase relationships, and then a couple of words at the end about permeability. I think this is going to take me a little bit over an hour. But then after that, as you know, there is Q&A, and you can add questions to the Q&A feature at the bottom of the view whenever you wish. And also there will be a bit of a quiz at the end, and the questions in the quiz will be based on the content of this webinar. So I hope you'll have a go at that. Nothing very, very difficult, but maybe quite interesting. Anyhow, if we want to understand about soil behavior, a really good place to start off is on the beach, and that actually is Kuta Beach in Bali. And I'm interested in the area of sand there where you see it's a little bit wet on the surface. And you can go walking or jogging down there, and I don't know if you've ever noticed something about it. So let's just have a look at this. So there is this sand with this film of water on the top, and down comes your foot. And when you first do that, two things. First of all, the area around your foot goes dry. In other words, the film of water disappears, and it feels hard. It's really interesting to try that out one day if you're walking down a beach in that particular location. And then when you lift your feet up, you'll see a little film of water left behind. So let's do it again, just to be quite sure. So down goes your foot. And then with any investigation, you've got to be a bit careful about your boundary conditions. And in this particular case, something went wrong. So that was a failure, that experiment. So one last try. So there is the beach again, the sand. Down goes our foot. It goes dry. We get a dry area around the foot. It feels very hard. But if we then wait just a few seconds, we start to feel the sand getting softer. And we wait a little bit longer and we slightly wriggle our foot, and our foot can simply disappear into the sand. It's a very major change in properties. And this was a successful experiment, but can you explain it? In fact, hidden away in that behavior are quite a few important principles of soil mechanics. And we'll certainly try during these webinars to talk about most of them. But it's not quite the end of the story, in fact. That was Kuta Beach. And if we travel to the east about 120 kilometers, we come to a very interesting beach on the island of Lombok, Tanjung Aan. And when you look at the beach, it looks much the same. We have the sea at the end. There's some swimmers, no surfers this time. But if you try walking down this beach, it's almost impossible. And you certainly couldn't jog down it. So there's another question. Why is that the case? So something else we need to explain. So let's have a look at the sand in detail. And here we are. So this is Tanjung Aan sand. That picture's about 45 millimeters across. And what we can see is that the sand consists of these perfectly spherical little balls, and they're all much the same size. In fact, it's what's called an oolitic sand, and they're quite rare and really extraordinary. But when we look at Kuta Beach, the sand looks like this. And if I zoom in a little bit to make it a bit easier to see, then when we look in detail, the sands are quite different. And we can see very clearly now those spherical oids or oolites, as they're called, from Tanjung Aan. But on Kuta Beach, we have a variety of mineral types, a variety of particle sizes, quite angular. They're slightly rounded by the action of the sea. And not surprisingly, we've seen that the performance of those two sands is really quite different. So looking in detail at soils to help understand these sorts of differences, an important part of soil mechanics. A few words on origins of soils. These are words that you will often hear. So let's be quite quick about this. You will be able to download a PDF copy of these presentation slides after this event. So you will have all of this information if you wish to have it. But there are normally 8 and I've got 2 slides. So on the first slide, we have 4 items there: residual, alluvial, colluvial, and glacial. Well, of interest here in Indonesia, it's the first 2, residual soils and alluvial soils. So let's spend a little time thinking about those 2. Residual soils come from the weathering of rock or other soils. And one thing that's rather important about this is that they can be very variable depending on the degree of weathering. And also their particle size can also be very variable. It can vary from clay to boulder sizes. So these are soils that can have a lot of surprises in store for you as an engineer when you're using them. Alluvial soils have been created by transportation and deposition by water. And what this tends to mean is that they're quite well sorted. They're often a little bit rounded, like we saw just now on the beach. And therefore, their behavior is likely to be very different to residual soils. And that's indeed the case. So in Indonesia, two of the most important soil groups are residual and alluvial. The other two of some importance, but I won't read through anything on those today. The other group consists of aeolian, which are windblown, organic, volcanic, and evaporites. And it's the middle two of greatest interest here. Organic, principally decayed vegetation. And of course, the famous deposit there is peat. We saw that earlier on in a picture. And then volcanic, these are soils that are being ejected or created by ejection from volcanoes. And we see things like lahars, which are granular soils. And when they weather, they actually become residual soils, and they can produce some very unusual clay minerals, which we will also look at briefly as we go through this presentation. One other thing I think it's interesting to be aware about, especially when we look at the marine clays, all around the coastlines, or around many of the coastlines of Southeast Asia, for example, the north coast of Java, parts of Sumatra and elsewhere, we have these marine clays. Also, for example, if you're from Malaysia or Singapore, you'll be very familiar with the marine clays. And just a couple of minutes on these, because they are such important deposits and they affect many infrastructure developments, because they are all around the coastline where we have flat land near the coast where we might want to make developments. And one thing that's really important is the effect of sea level changes in the deposition of these clays. And the two main ones we normally think about are the upper and lower marine clays, which we find around the coast of Southeast Asia, and it's strongly related to sea level. Now, that graph you see there is a diagram of sea level over the last 900,000 years, and it's going up and down. And of course, the low parts are where we have a glaciation, and the high parts are where we have an interglacial, where we are at the moment. So to make it a bit clearer, let's just look at the very early part of that graph. And here it is. So we now have a vertical axis, which is the sea level relative to today. And we have thousands of years along the horizontal axis. And you can see that same shape. But what's important here is that, first of all, you can see that sea level has been much, much lower in the past than it is today. Even say about 18,000 years ago, it was 120 meters lower down. And of course, this affects deposition of marine clays. And in fact, the only possible times when they could have been deposited are indicated by the yellow and red bars, which you can see up at around about the sea level. So that is the point in time when they could have been deposited. What this also means is that the upper marine clay, indicated by the red line, when it was deposited, is very young. And I have this really very nice picture, which was taken from some sampling I was involved with in Singapore a long time ago, but it's a Delft continuous sample taken right through the marine clay deposit in Singapore. And it would be very similar if you did it here in Indonesia. So what we have down at the bottom there is about 120,000 years ago, and the sea level was high, so a marine clay could be deposited, and we call this one the lower marine clay. But at the top of it, what happened then between 10 and 100,000 years ago, the sea level dropped and that became a land surface. And the reason why we see all that coloration is that we get oxidation going on from the effect of sun and weathering at the top of the deposit. And in fact, if you look at the very top, you see that dark brown color, that is an old topsoil. So that was an old land surface. And then we had the end of that glacial period. The sea level rose quite quickly, and then we got deposition of the upper marine clay. And that was deposited between 3,000 and 8,000 years before present. And you can see there how we have shells in the bottom, and then we have a more uniform looking material as we go further up. So this is a very nice calibration of what we see when we look at samples and so forth in the marine clay. And I think it's quite interesting to see that. One important point is that if you're standing on a site which is underlain by marine clay, like this one in Malaysia, and what you can be sure of is if that is currently above sea level, deposition ceased about 3,000 to 4,000 years ago. And that is quite an important thing to realize. So if we look at detail of this, at the end part of this period, where we have thousands of years ago on the top, and we have relative sea level on the vertical axis, then the only possible deposition time for those clays could have been around about what was called the mid-Holocene high stand, when the sea level was higher than today. It's the only way you can have a marine clay deposited at a ground level which is higher than the sea level today. So one important point to ask, whenever you're looking at profiles of soft clays, which we often do in this part of the world, it's important really to understand whether or not they're marine clays, because then you'll have an indication of their likely properties. And an important question is, what's the ground level? Because if the ground level is more than about 2 or 3 meters, it's really not possible that they could be marine clays. They would have to be formed in some other depositional environment. So this is slightly associated, but there are some important terms that we often see in soil mechanics: normally consolidated and over-consolidated. And I thought it was worth spending a couple of minutes looking at this and seeing how it affects soils. So it's all to do with stress history. So let's imagine we have a site a long time ago, and we have a soil sample down the bottom there, the little blue square. And at that time, there's a certain depth of burial, H, and a certain water level. And from that, we can calculate the vertical effective stress. And because it's the maximum that this soil sample ever felt, we'll call it max, sigma dash max. Or we can call it the pre-consolidation pressure, which we'll come to in a minute. So time goes on, and through some geological process, the ground level drops. Material is eroded away until we get to today. And if this is the situation today, then the vertical stress on our sample has become smaller. And there's a rather important ratio between that maximum value in the past and today's value, which we call the over-consolidation ratio, which is simply the ratio of those two values. And this is a very important thing to know about when you look at soils, whether they're soft soils or other types of soil. This is something important to understand. Something else we'd like to know, especially if we're doing finite element calculations, is what's the horizontal stress? And the horizontal effective stress is related to the vertical one by what we call the earth pressure at rest. And we use a particular symbol K0, which is the ratio of the two. It's the ratio of the horizontal to the vertical effective stresses. And this K0 value is strongly related to the OCR, the over-consolidation ratio. And there are a number of ways you can measure PC- for soft clays. We can use the odometer, which we'll see in a minute. But this is not so easy for stiff clays. And I'm going to use here an example of the London clay. You might say, why London clay? Well, I studied in London. I think it's reasonable I should do that. So let's have a look at that. So this is a profile of the K0 value measured in London clay by a variety of techniques at a variety of locations around London. And you can see that K0 is very high. This means that the horizontal in situ stress is much higher than the vertical one, up to 3 times. And it's been measured in a number of ways, but what's important really are the values that we see. Now, what I can do, I can relate that to the OCR using an expression like that. There are many variants on this kind of expression. They are empirical in nature, but they still give us an idea. So I can then translate that into OCR, the over-consolidation ratio, and you can see that it's very high, up to 100 times at the top of a deposit of something like the London clay. So that's a heavily over-consolidated clay. But if we have a site where the current stress is the same as the maximum part stress, OCR is 1, and then we call the soil normally consolidated. So we can determine this quite nicely from odometer tests. And here I have a profile of the over-consolidation ratio for a Holocene marine clay. It's actually in Malaysia. And you can see there that the values, once you get below a desiccated crust, the values are very low. They're actually close to 1. And those are determined from looking at the results of odometer tests. And I can then transfer that to K0 using that same sort of expression. And you can see there the K0 value, again, once you get below about 2 meters, is around about 0.8. And this is very, very different to London clay. If I quickly jump back to the London clay profiles, just to see how different they are. The scales on the upper axes will remain the same. Here we go. There's London clay, hugely different. And this probably is a very, very good clue as to why those two clays have significantly different properties. And we might have a question about that later on as well. You can also get over-consolidation taking place due to a rise in the water table level. Not huge effect, but it can happen. But one thing to be aware of is that this whole concept of normally consolidated and over-consolidated really only applies to alluvial soils and maybe glacial ones where you had the weight of a glacier on top of them. But in many of the other soil types, it doesn't really apply. And it's important to realize that, because sometimes people try to use this idea of over-consolidation ratios, say, in residual soils, and it doesn't really work very well. So just a few summarizing words here. Stress history in soils is very important, especially if you're using finite elements to model them. And true normally consolidated soils are not often found. Most soft soils we see, like the marine clays, would be very lightly over-consolidated. We can find under-consolidated soils, and they're generally in things like river deltas, like the Mahakam Delta. The deposition going on there would be creating some under-consolidated soils. And it is also possible to find heavily over-consolidated soils near the ground surface, like London clay, and they're quite stiff. But this terminology can apply also to sands, although it doesn't have such an marked effect. And just to remind you that it is principally applying to the alluvial or sedimentary soils, this whole idea of over-consolidation ratios, and so on. I mentioned that already. Stress history, when you're doing FEA, finite element analysis, it's important to get that right in your foundation soils. A few words now about geotechnical site investigation. I'm not going to go into this in detail, but it's just a few words, and in later webinars, we'll have a look at a bit more detail in some techniques for doing site investigation. But the main target is to find the distribution of soils at your project site and the appropriate, or the soil properties appropriate to the structures you're designing. That is kind of important, because you can spend a lot of time and money testing soil properties, and then you find out they're not useful. So you need to make sure that what you're measuring is what you need to know for the particular project or the structure you're going to design. Of course, we want to get the best possible results. We want to keep costs as low as possible, and we want to do it quickly, because no one wants to spend too long on site investigation. This can all be optimized, and some of the techniques we'll talk about in a later webinar will look into that. Of course, one quick source of data is to have a look at geological maps and other published information. This can be a very useful source of data, and there we can see part of the north coast of Java. And if you look at the legend on the right, you'll see mention of Holocene deposits and other ones. But probably what most of you will see is geotechnical reports. And I think really these webinars are aimed very much at engineers who receive geotechnical reports, and then they have to make use of that data in their project and in their designs. So there are normally two types of report. There are factual reports, and these give descriptions of soils and measured parameters, borehole logs, maybe the results of in situ and laboratory testing. And it seems to be the case, especially in the good old days of paper versions, that there was a target to make these as thick as possible. Therefore, one important skill is making a very good summary of the information in these factual reports. The second kind of report is an interpretative or engineering report. And here, what should be happening is that the author takes the factual data and gives you an interpretation of the important parameters. For example, like the undrained shear strength, C' and Phi'. They may give comments on stability of slopes and foundations, or provide you with allowable bearing pressures. And also in these reports, you frequently have large tabulations of data. And the only point I want to make here is that if you're an interpreter, if you want to use this information, it helps greatly if you can summarize this into a small number of plotted profiles or similar graphs, because you can see everything so much more quickly. And that is something which we need to look at briefly. So to give you an idea, something like this. This is a very nice series of profiles of properties for a Holocene marine clay. There are 4 of them there: the Atterberg limits and water content, then undrained shear strength, pre-consolidation pressure, and compressibility. Now, this information could quite easily occupy 1,000 pages of a report. But in one slide, in this case, you can very quickly see what this site looks like, what the properties look like. And if you're designing, say, an embankment over that clay, you have all of the data you need to go ahead and do that. So the skill of doing this is important. With these days, we have wonderful programs like Excel, where it's fairly easy to put this information into those programs and derive that kind of result. Now let's move on a bit now and talk a bit more about soil parameters. And as I said, I'm particularly interested in reinforced fills. So I'm just mentioning them and showing you a picture there. So obviously, when we're designing any kind of earth structure, with or without soil reinforcement, the properties of the fill are going to dominate its behavior. So we need to understand them well. Therefore, it's important that we take adequate samples and we carry out appropriate testing. And that's what we'll start to look at now. Here's a nice sample of soil. It's actually a piece of weathered granite from a site in Malaysia. And it's made up of a number of different particles: mineral particles, rock particles, maybe clay minerals, maybe some organic material. So if we look inside it and we look at the particles, we're going to have some large ones, and then some smaller ones, and some even smaller ones, and some very small ones. And a very nice way to summarize that data is to carry out what we call a sieve analysis, where we use sieves, which look like this. These are very nice clean ones because they're from a catalog. And we pass the soil through there to find out the arrangement of the different particle sizes. And if we're lucky, we have a thing called a sieve shaker to do it. Now, sieve shaking, or the sieves are used basically for the sands and gravels down to 0.06 millimeters. So, and the particle sizes give us the principal names of the soils. So we have here boulders, cobbles, gravel, sand, silt, and clay, and they're each determined by the range of particle size, which I don't need to read out there. But just to make a point that this is one particular system, there are other, you can find other systems. So for example, the very important boundary between the sands and silt, which is between the coarse and the fine soils, that can be different. You might find it in other areas, like at 0.075 of a millimeter, for example, in the US system, but it's not very different. We normally then subdivide, so we get coarse, medium, and fine in the gravel, sands, and silts. And in this particular system, again, it's easy to remember because it's all 2s and 6s. So if you remember that the top end of the sand range is 2 millimeters, that's something you can kind of see, really, then everything else follows from there, and it's quite easy to remember if you need to, those various ranges. So if I add some data here from 3 samples, I've got a green sample, a brown sample, and a blue sample, I can arrange them in that way, and that's quite interesting. But far easier is to plot this on a special kind of diagram, which we call a particle size distribution curve or a grading curve. And this is how I like to do it. So we have the particle size along the bottom on a logarithmic scale, and then the percentage passing the sieves is on the vertical scale. And one little point to make here is that when you have these graphs, it's really helpful to add the names along the top. So often I see these graphs without them, and then you have to kind of think a bit, oh, where is the difference between sand and gravel? But add the names, and then instantly you can see that the green the green soil is a uniform coarse gravel, the brown one is a well-graded sandy gravel, and the blue one is basically a fine sand with some medium particles. So easy to see when the names are placed there. One little warning that in some reports, you'll find these plotted the other way around, especially in US practice. It doesn't really matter. You just have to kind of think of them backwards, but it has the same effect. And here are some pictures of some coarse soils. So this is quite unusual to see undisturbed samples of sand. And you've got here some medium and coarse sands sampled actually in a site in the UK. But these were taken with a special kind of sampler, the same one as I used for the marine clay earlier on. And you can actually see what the sand looks like in an undisturbed form. Not easy to do that. Some other terminology now, uniformly graded. We use that term when the particles all have much the same size, like we had on the beach in Lombok. This particular picture shows it's a railway ballast, which is a man-made aggregate. But if you have single-size materials, they're not very good as fill materials. The other picture at the lower half of this slide is a well-graded soil, where we go from fine soils all the way up to coarse ones. And generally, well-graded soils are much better as fill materials. And then there's the angularity of the particles. Top picture, that's a crushed material. So the particles are extremely angular because they've been crushed by a machine. But the lower one we saw earlier on, that's a river gravel, and it's extremely rounded because the stones have been rolled along maybe for many, many kilometers by a river, and it makes them very rounded. And of course, a rounded particle, not so good as a fill, whereas an angular particle would be very good to be used as a fill material. So these are all important little details that help us make assessment of the usability of these sorts of materials. Now let's move to finer soils. So again, using that tabulation, I've got a green, brown, and blue soil again, and I've done it in numbers there, but let's look quickly at the particle size curve because it's much easier. And we can see now that we have a green one, which is mainly a sand with a bit of silt in it. And then the brown one is mainly silt with a little bit of clay in it. And the blue one is mainly clay with a little bit of silt in it. So that gives us the names which you can see there in the legend. So for the coarse soils, which we normally separate between fine soils and coarse soils, the coarse ones are the sands and gravels. And those ones we can investigate using the sieve analysis. But when we get down to the finer soils, we can also use a technique to measure their particle size. It's a bit more complicated and not such an easy test to do, but to be quite honest, I would have to say that if I had to make a choice between Atterberg limits and measuring the particle size of fine soils, I would use the Atterberg limits every time, because these Atterberg limits tell you a lot about the nature of the soil. And when you're looking at clay soils or potential clay fills, the first thing I like to find out is, what are the Atterberg limits? And these are very useful little properties to help us understand better how these soils are likely to behave. One thing to mention now is that the reason I have a dotted line there halfway along this particle size curve is that's at 0.425 millimeters, which is halfway through the sand sizes. The reason I mention that is that when you do Atterberg limits, you have to remove all particles greater than that. So there is some preparation required in many cases. So you could carry out an Atterberg limit test on the green soil, but you'd have to remove the coarser material first. That is something to be aware of later on, and I'll mention it again when we look at data. Clay fills, yes, perfectly acceptable. In many situations, of course, we're going to use clay fills for highway embankments and so on, often for reinforced soil structures as well. We need to be aware that, in particular, some clays can suffer a lot of volume change, say from wet seasons to dry seasons. So they can change their volume, which means that they will deform. And if this is a problem, then maybe they're not such a good one to use in some situations. So you need to be aware of that when we look at clay fills. This is actually the wonderful tanah merah that we have here in many parts of Indonesia. It's a clay fill derived from volcanic material. It has particularly good properties. We'll mention that again in a second. Any kind of presentation like this wouldn't be complete without a few pictures from an electron microscope to look at these things. So these are clay minerals. The clay minerals are a very special set of minerals. And what you can see straight away is, first of all, they're very small. So that is a scale bar there of 1 micron. That's 1/1000th of a millimeter. And they are very small. Now, there are 3 main clay minerals that we talk about: kaolinite, illite, and montmorillonite, which are sometimes called smectites. And generally, the particle sizes are getting bigger as you go from K to I to M. So with my little K, I, and M over there on the left, I put an arrow there to make a point that generally, as you go from the kaolinite through illite to montmorillonite, the engineering properties are becoming, I'd say, worse, more compressible, lower phi values. You get into the area of the swelling soils, especially with montmorillonite. So it's quite important, if you possibly can, to know about that. And to show you, back with our good old friend London clay, this is a distribution of the clay minerals in London clay. And you can see the blue color is smectite or montmorillonite. And this is why London clay actually is a rather difficult soil. And if you've ever had a house on London clay during a dry summer, you tend to get all sorts of problems because of desiccation and drying out of the London clay. So I know not so relevant to Indonesia, but relevant in general to soils. So understanding something about the clay mineralogy is helpful when we look at clays. So here we are. This is an Indonesian soil. This is somewhere near Surabaya. It's a very expansive soil. You can see that from the wide cracks on the surface during the dry season. And that can cause problems because it allows water to get deep into the soil. And you can see here how we have a very low angle slope failure going on. And that's been caused by the nature of these expansive soils. A few more electron micrographs, but there's some quite interesting ones here. This is the marine clay in Singapore, Kalang Formation. And we can see nicely there, again, we've got that bar to show you this scale, 4 microns along there. And you can see a variety of particles. So we can see lots of little platy particles in a kind of very variable arrangement. But we also see what I call a loaf of bread, the bit in the middle, where that was probably a larger particle that has been weathered and reduced to a series of clay plates. So the clay minerals end up being these plate-shaped, having this plate shape. However, we do find other kinds of small particle in the marine clay. Those little almost circular particles are actually what are called pyrites framboids. They're tiny. I don't think the content is that much within a marine clay, but obviously they would affect the behavior. So more that this is the marine clay from Jura. We saw information about its over consolidation just now. You can see it looks quite layered when we have a general view, but when we look a bit closely, we start to see some interesting things. And this is the case in many of the marine clays around Southeast Asia. We find diatoms. Now, diatoms are basically they're silicious fossil skeletons. So they're made of silica. Silica is the same as quartz, of course. And in this particular case, this clay had up to 60% content of silica, which is very strange for a clay. And this clay has a liquid limit of 120%. And when we did some effective stress testing, we found that the phi value was 30 degrees. Now, if I tell you that we have a marine clay with a liquid limit of 120 and the phi is 30 degrees, you first of all would say that can't be right. But it was correct. And it was correct because of this particular situation with a very high silica content. It's not the same in every marine clay. In this particular location, it was. So here's a little bit of kind of advice that when you see data that is unusual, definitely important to question it. Investigate it. But sometimes you need to be ready for something that's unexpected. And this is certainly the case in this particular marine clay. Here's another clay mineral, and it's a very special one to parts of Indonesia. It's called halloysite. It's also a relative kaolinite, but it forms these tubular shapes. Now, a couple of things going on here. First of all, you can imagine that these tubes all locked together could give a pretty good strength behavior, and indeed they do, but also they can hold a lot of water. And that's actually the case. We have a special name for this clay around Indonesia. We call it tanah merah, or red soil. And in this particular soil, the phi dash can be quite a lot higher than 30 degrees. And we can use it for fills. We saw this earlier on in a photograph, and it can make extremely good fill. So that is a clay of volcanic origin, because when these volcanic materials weather down, they tend to form this type of clay mineral. Now, one way we look at these Atterberg limit results is to, or the clay minerals, is to measure the Atterberg limits. And the Atterberg limits, as I mentioned earlier on, they are carried out on the particles smaller than 0.425 millimeters. So if we have a graph like this, where the horizontal axis is the water content and the vertical one is the remolded strength of a soil, maybe you've got it in your hand, then if you have a low water content, it'll feel quite stiff, but you can still mold it. And that would be something close to the plastic limit. But as you add more and more water to your sample, it becomes softer and softer until it essentially becomes almost a liquid. And we call that the liquid limit. Of course, we have specific tests for doing that. I'm not going to tell you how the tests are done today, but the difference between the two we call the plasticity index. Now, these are these very useful numbers that give us some indication of the likely behavior of these clays. Sometimes we call, I've shown there these values as WL and WP, but sometimes people call it PL and LL for short. It's up to you. They have the same meaning, but don't forget they are water contents, but they're water contents at a specific condition. But we never put percentage after them. We just say liquid limit of 100. We know that means 100% water content. Here are some examples. We have here the upper soil, which is a sludge and probably pretty close to its liquid limit. It actually flows. And the lower picture is a compacted tanah merah, where that would probably be very close to its plastic limit when it's just right to be compacted into a structure. The way we normally summarize these Atterberg limits is to plot them on what we call a plasticity chart or a Casagrande chart, where we plot the plasticity index versus the liquid limit. And then we have this rather well-known line called the A line, which is the inclined line on the graph there. And I've shown here two test results actually from the United Kingdom, a glacial till and London clay. And the point about this graph is that if you plot above the A line, then the material is likely to be a clay, but if it plots below the A line, it's likely to be dominated by silt content. And that's why we have this terminology CL and HL, ML and MH, sorry, CL and HCH, ML and MH. And you often see those names appended to soil descriptions, a CH soil, clay of high plasticity. And that tells us something about the likely behavior of the soil. There are some more complex systems than this one where you have many categories, but I'll just show the simple one here. One other system which we can sometimes come across is the AASHTO classification system, where we have things like A76, A75, and so on. And it's very close to that other scheme with the A line. So an A76 soil would generally be very similar to a CH soil from the other system. Here's the diagram showing you what the marine clay looks like. The marine clay is a clay, plots nicely above the A line with a few minor exceptions there. And here we have some interesting soils. These are all clays, and they're all residual soils, in fact. But what's important here is that they are not following the normal rules. And you can see there we have three clays. We have black cotton soils, which are essentially montmorillonite, or rich in montmorillonite. We have the red Tanamera clays, where we have a lot of this halloysite clay mineral. And we also have allophane clays, which is another interesting type of clay derived from volcanic material. The point is that the red clays and the allophane clays plot well below the A line, but they are clays. So the point here is that the derivation of these ideas has come principally from alluvial soils. And sometimes those distinctions don't apply very well to soils with other origins. So we need to be aware of that when we look at this data. So if you looked at that blue material and said, oh, that's a silt, in this particular case, you would definitely be wrong. By far the best way to plot this data in a profile is like this. You saw it earlier on, but I'll just show you in a bit more detail here. So we plot the Atterberg limits as a bar, a horizontal bar with plastic limit at one end and liquid limit at the other end. And then we plot the water content as a series of dots, which if you like, you can link together. But it gives you a very nice quick picture of the nature of this soil. And you can see here that at around about 6.5 meters, there's a very distinct change. And in fact, the soils become much stiffer. And one way we can actually put numbers on that relationship is by what's called the liquidity index, which is the ratio of the water content minus the plastic limit over the plasticity index. And essentially, it's the distance that the water content plots either side of the liquid limit. And it's just a nice way to put that into a single number. There are some information, obviously, which you can work out for yourself. But here's an interesting question. You'll see there are 2 points there where we have a water content higher than liquid limit. Question, is this actually possible? And the answer is it most certainly can happen. And it often happens in very sensitive soils, but there could be another reason. And I just want to show you what the other reason can be. So here is some work that was done to look at Atterberg limits and the effect of preparation, because I mentioned earlier on how we have to remove coarse material from the samples, which means you end up with a slurry or almost a liquid with the remaining soil. So you've got to dry them out. And they can be dried out in a number of ways. Or if you're lucky and you can use the material in its natural state, then that's better. But you can see what happens, any particular sample, as you go from natural to air dried to oven dried, the Atterberg limit values are moving basically to the left and down the diagram. So you're going to get different results. So we can have any of those three methods of preparation and they can affect the results. They can have a major effect. These are residual soils, these particular examples, and this graph is showing the same behavior for alluvial soils. So one point I'd make here is that when you're looking at Atterberg limit data, it's very important to be aware of how they were prepared because it can affect the results very significantly. So I would like to see this. If I'm looking at a tabulation of Atterberg limit results, two things I'd like to know. What percentage of material passed the 0.425 micron sieve, and how was it prepared? Because this would help me interpret the results. Unfortunately, I'd have to say, unless you really hunt back through the original laboratory data, you don't normally find that. But of course, if you're specifying a site investigation, you can ask for that information to be provided. And I'd recommend that you do. So let's just look at the last little thing on Atterberg limits. Let's look at a couple of profiles, some real profiles, and we'll go back to our friend London Clay. So there is a really nice profile of the Atterberg limits and natural water content of London Clay. And you can see that the water content plots very close to the plastic limit. So it's down at the left end of each of those bars. And then, not surprisingly, we expect that soil to be quite stiff. If I now compare that to the actually profile we saw earlier on, but this is a Holocene marine clay from Malaysia, then you can see now that the water content is plotting right over by the liquid limit. So these are clearly two very or these are two clays that are going to behave very differently, but they are both marine clays. And as it says at the top there, the difference is the London clay is extremely old and has a lot of stress history, whereas the Holocene Juru upper marine clay is very young, and the stress history is quite simple. So this could be a possible question for you. We have a sample from a depth of 2 meters in both of those clays, and there's a water table or phreatic surface at 1 meter, and they both have C' of 2 kilopascals and phi dash of 26 degrees. This is very possible. But the London clay has an undrained shear strength of 100 kilopascals, and the Juru clay has an undrained shear strength of only 8 kilopascals. Can you explain that using soil mechanics? So this is a rather important thing. And again, there might be a hint there of one of our quiz questions to come a little bit later. We have soil classification systems where we take things like particle size and Atterberg limits and we classify them. I'm not going to spend any time on them. These are things you can find in soil mechanics books and other documents. I did mention earlier on the AASHTO classification system, which, although not a mainstream one for geotechnical engineers, because it's aimed at pavement and highway construction materials. Actually, I quite like the AASHTO classification system, but get to know them, be aware of them. If you never know what you're going to see in a report, and if someone says they've got an A75 soil, you shouldn't be surprised by that. You should realize, oh, that's from AASHTO and it's just below the A line. So don't be surprised by that. So be aware of the systems being used in your country or your location, or what's being used in particular reports that you are looking at. Last little thing to look at for a few minutes is a bit of, if you like, undergraduate soil mechanics. It's to look at the soil phase relationships, but these remain incredibly important. And if we have a kind of a nice image through some soil there, where the brown particles are obviously the solid bits and the white is the void, then we have this very important parameter, the void ratio. And the void ratio is simply the volume of voids divided by the volume of solids. And for me, that's something I always want to know, especially when I'm looking at the more compressible and softer soils. I'd like to know the void ratio. In one number, it tells you a great deal about the soil. Of course, those voids might be full of water. And if they're completely full, we call them saturated soils. Now, when it comes to thinking about our fills and our engineering use of soils, then a saturated soil would not be very good as a fill material. It would be very difficult to handle and place. So no, we don't want our fills to be saturated. Much more likely, especially in a fill, is that we have little air bubbles or quite a lot of air in it, which are the little white bubbles now. And then we say that the soil is partially saturated, which will be the case in most fills. And that's a good thing. We want our fills to be partially saturated to improve the way they compact when we place them. The famous water content, simply the weight of water over the weight of the solids. I think we can all remember that. And then another one is the degree of saturation, which is simply a measure of the amount of air in a sample. And it's the volume of water divided by the total volume. So if it's 100%, it's saturated. And if it's 0, it's dry. And then the way we try to understand these, and again, very much undergraduate soil mechanics, but we have this nice little phase diagram where we divide our soil into air, water, and solids. And then by having a sample of some sort, we can measure the total volume and the total weight of the sample. We know that the weight of air is 0. So we can then find out the weight of the water by drying it out and finding out the difference between the weight of the total weight and the weight of the solids. Then the other thing that we will measure in a soil is what's called the specific gravity, which essentially is the density of the solid particles related to the density of water. So typical number, 2.6, 2.7, something like that. We know for most soils it's going to be in that order. So we can then take these relations and we can make these simple expressions. We know that the volume of solids, we can calculate that, taking into account specific gravity. The volume of the water is easy. And then we can find out the volume of air by doing that simple subtraction. So this gives us the components of a soil sample, and we can then derive other things from them. Now, you need to be aware that when we get soil data in our reports, we only basically get three things that are measured. We get the density or unit weight, depending on how it's expressed. We get the water content. Of course, we're always looking for that in our report. And we get the specific gravity. And everything else, like void ratio or porosity or whatever it is you want to know, degree of saturation, is going to be derived from those three using some of those clever relationships. Now, I want to show two of these to you. I'm not going to try to explain them. If you want to look at these, you can look at them later on when you get a copy of these slides. But let's have a quick look. Example one then is to find a relationship between density and what is called dry density. Dry density is not a real thing. It's an imaginary density where we imagine that the water is missing. And we tend to use that when we look at compaction testing. And by playing around with those various relationships, we find out that the dry density equals the bulk density divided by 1 plus the water content. Now, that's an expression that's worth remembering, especially because if you're looking to find unit weights of soils for your designs and you go to the compaction testing, those densities will be given as dry densities. So you need to convert them then into bulk densities. The second example is a bit more complicated to do, but it's not that difficult, is to find a relationship between water content and the unit weight, taking into account the degree of saturation. And you can do that by playing around and doing a bit of algebra. I'm not going to go through that, but you end up with that expression at the bottom there. And this is a really useful expression when you are checking test data in reports. So let me explain how. So you can plot a graph of that expression, and I've plotted it there for a specific gravity of 2.63, and then you can add data from reports onto that. In fact, when in my very early days as a very young engineer, I can remember having that plotted on a piece of graph paper beside me, and when I looked at reports, I would quickly just check to make sure that data seemed to be in the right place. Now, that blue data is all very well behaved. The right-hand dot's very close to fully saturated and the other one's not quite. You'd have to say, well, did they come from below the water table, those samples? Should they be fully saturated? So quite a useful thing to look at. Here are some typical bulk unit weights. In most fill soils, they're going to be in the upper teens or low 20s at the most. I think we know that, but there's some typical values for you to take into account. But just that warning again, if you're using compaction test data to find bulk unit weights for design, say of a slope, then please convert it into bulk density using the water content. But two examples of how this can help you. Say I plot my information and I get those 3 points well above the brown line. That's a bit suspicious. They can't really be up there. So maybe there's something not quite right with those samples. The water content is either far too high or the density is far too high, one of the two. So maybe you need to investigate those samples to see what was going on. In this particular case, let's just imagine that those samples all came from below the water table and you're relying on those samples, say, to measure the undrained shear strength. Then you have a bit of a problem there because 3 of them have dried out. They have a lot of air in them, and therefore you have to be very suspicious that you wouldn't rely on too much on tests, say like an undrained shear strength test carried out on those 3 samples. And then the last thing I said I would mention would be a few words about soil permeability. No more than that at the moment, it's just a few words. But what I would like to do here is just to try and demystify the numbers, because permeability is given by a parameter K, and its units are meters per second or something like that, but it's a speed. It's a measurement of speed, and it's the speed at which the water can flow through the soil. And I've put 4 different soils down there and also their K values: a uniform gravel, a beach sand, maybe from Kuta, a silt and a clay, and the numbers become incredibly small to the extent that they're really rather difficult to see their meaning. When I tell you that clay has a permeability of 10 to the minus 10 meters per second, you might say, whoa, that's obviously very small. But I have a way of thinking about this, which is a little bit easier. So take that away. And basically, it's the time for water to travel 1 meter through this soil, but under certain conditions. So if I take a tube of the soil 1 meter long, and I place another tube full of water at one end of it, so the water can travel through the horizontal tube, and I let the water travel like this and drop out at the end, then the numbers there, those times, 2 seconds, 17 minutes, and so on, that's how long it would take. And you can see that in the case of a clay, over 300 years to travel through that sample. Of course, what this means is that clays are effectively impermeable. And of course, these numbers become incredibly important when we start to look at any analysis to do with the time effects of consolidation and so on, using finite elements or whatever techniques you want to use. So understanding permeability and getting the right values is extremely important. But that's just another way of thinking about what those numbers mean. So just remember, clay, 1 meter thick, it takes about 300 years for the water to travel through it. So highly, highly impermeable. That's where I come to an end. I think I've gone just slightly over an hour, which I thought I would do. Just to remind you that we plan more of these webinars. And the next one in March will be on a topic which I feel quite strongly about, which is measuring soil shear strength using the shear box and looking at the do's and don'ts of that particular technique. So I'll dedicate a single webinar to that because I think it's so important, and that'll be the next one we do during March. So I would just like to thank you for listening. You've had a chance, I think, to put questions into the Q&A section of this. So I think what we're going to do now is to start to look and see if we have any of those questions, and I'll try to deal with as many as I possibly can in the time available. Right. So I haven't had a chance to look at any of these yet because I've been speaking to you, but we have here something like 31 questions, and they're partly in English and partly in Indonesian. So I will try and pick a few of these, and let's have a look at some of these. So let's just start at the top to begin with, as we have a first question there in English, which is going to be a bit easier for me. So as we know, if the consistency of clay is stiffer, it will have the higher value of density. And in another location, especially the Java Sea, we have seen another behavior of soil with a consistency of stiff, and the density was 1.5 to 1.6. Would you like to explain this? Well, yeah, that's a very good question. We can have stiff soils which have lowish density. It is possible. We simply need to look at all the different elements that are making up that soil. We need to understand the clay minerals. We need to understand what we can about the soil. It is possible. Generally, when we go down to those low densities, we expect soils to be softer. It's not always the case. And I think I can't give one simple, quick answer to that, but just look at all of the various properties involved to make sure you understand why. One type of soil where this can happen can be quite difficult is when we have very sensitive soils, and very sensitive soils can become quite stiff, but they can have quite a collapsible structure, and therefore they seem to be stiff when they are when they are undisturbed. But when you disturb them and remold them, they can become very, very soft. And maybe a soil, that could be a soil of that type. So we have something out of the topic. If it's out of the topic, I might move on a bit. This is to do with ENG. I think I'll move on to another question. That could be for another day. We'll keep a record of your questions. In fact, I've got them here. In fact, I've got them printed. So, oh yeah, right. So we are. Oh no. Right. penelitian karena efektif yang total kapan digunakan masing-masing kondisi digunakan stabilitas. Okay, if I get this right, this is about effective stress and total stress. This is actually going to be a subject of another webinar. I'll just make a summary comment at the moment that getting this right is extremely important. Most geotechnical analyses really needs to be done in terms of effective stress. But there can be situations, particularly when we use more traditional analysis like limiting equilibrium, where we need to revert to total stress, for example, for foundation bearing capacity. But if we were looking, for example, at the stability of a slope, then it's most important that we take into account the behavior in terms of effective stress, especially if it's the long-term stability. I think you'll know that if you dig a steep bank in a clay, it can stand up to enormous heights. And I guess in those cases, you might say, well, the thing to do is to look at the total stress situation and look at it in terms of the undrained shear strength. But that's only a temporary condition, and it would be quite unwise to do that. So we need to be very careful and make sure we are applying effective stress and total stress at the right times and to the right forms of analysis. In the soil condition, only divided into saturated and unsaturated soil, is there a partially saturated? Oh, yes, of course. In fact, most fills are partially saturated. When we say unsaturated soils, that also means partially saturated. It simply means that, I mean, the condition of fully saturated is very clear. That means that we have 100% water in the voids. Once you start to lose some of that water and it's replaced by air or some other kind of gas, then we call the soil unsaturated. And probably some of you will be aware that there is a whole area of soil mechanics called unsaturated soil mechanics. It's not the soil mechanics of dry soil. It's the soil mechanics of soil where the void space has a mixture of air and water. And I'd have to say it does complicate things significantly. And I have planned a webinar to look at drained and undrained conditions where the significance of this hopefully will become apparent. I wish you would like to discuss with you about the problem of expansive soil. Yes, okay, well, expansive soils, yes, they are materials that can cause a lot of difficulties. In many situations, I did mention them in relation to London clay. London clay is an expansive soil which causes trouble for houses that are built on it sometimes. Also, along the north coast of Java, we have a lot of expansive soils, and they can cause trouble when we build roads over the top. I think probably in detail, that's a discussion for another day. But I'd have to say, perhaps I'll mention right now, in another series of webinars being organized by the Indonesian chapter of IGS, we shall have a talk from a gentleman called Professor Jorge Zornberg, who has a great amount of experience in expansive soils. That'll be coming up in about August. I'm afraid you're going to have to wait a bit. But he will talk about the issue of expansive soil. So I can a little bit deflect that question, but it's certainly a very interesting topic. Ah, this lady, I recognize her. How to adjust appropriately soil stiffness for drained soft soil. Wow, measuring stiffness of soft soils is not so easy. Basically, we have two test types we can use. We can use the triaxial test, or we can use the odometer. The odometer measures a particular kind of stiffness, which is because it's restrained, and the sample cannot expand laterally. Whereas, of course, in a triaxial test, you can measure the stiffness taking into account the lateral expansion. Those two, of course, are related by the Poisson's ratio. But when you say adjustment, there's not really an adjustment. It's something you really have to determine by testing and looking very carefully and making sure that you examine both the drained and the undrained conditions to look at those stiffnesses. This is to do with geosynthetic. This is to do with selecting geosynthetic in relation to soils, I think. Maybe that's a good question for one of our geosynthetics sessions as well. And I think Paulus did talk about that in a webinar a short time ago. I'm trying to remember SPT. Oh, SPT. SPT, the standard penetration test. That again, that's something we'll look at in a future webinar. I didn't talk about any particular in situ testing methods or explanations or interpretation today, but that's one we're going to come back to. I would like to talk about SPT because it is important. The SPT is used a great deal in geotechnical ground investigation, and I think, as you know, the whole problem is the S on the front. In English, the S stands for standard. One problem with that test is it's far from standard. Different people can do it different ways. This is quite a big discussion, and I know there's been some quite good presentations by people from HATI on issues of SPT testing, and maybe that would be a good source to find more background. But I will come back to that in a future webinar. So this, I think, basically is the condition of a soil after some time. Will it remain in good? I think the answer is yes. One thing that's really important, especially when you're using clay fills, is to protect them from the ingress of water. Right? If you like, one thing we want to do with clay. So if we're building a highway embankment from clay, when we compact that clay, there will be a pore pressure in it, and the pore pressure is going to be negative. It's going to be in suction. And one thing that's really important with a clay fill, unless the clay fill is enormously high, is that we protect and prevent that suction from absorbing water. So when we look at clay fills, which this could be the case, I think, then I think by far the most important thing after 20 years is that we should make sure that we arrange drainage measures so that water does not come in contact for any prolonged time with the clay. This is a really important point. Now, again, there will be a webinar dedicated to clay fills. I'm not quite sure which one. It's somewhere on that list. It was towards the end of my list of webinars. This is actually a topic which I would like to talk about because I think a lot of people misunderstand this. Clay makes very good fill, but we need to be aware that on compaction, basically it wants to absorb water if it's been well compacted. And if that's the case, the main target for your design needs to be to protect it from the effects of water, either under or around it. Of course, rain is going to fall on your embankment, but it doesn't stay there very long. And due to the very low permeability of clay, the occasional submergence in water doesn't matter. What's important is long-term contact with a source of water. That's when things can go wrong with clay fills. I'd love to talk to you about strengthening soils with Tensar products. It's not really, there we are. It's from this young lady who I know very well. I think for today, not really the topic, but it is certainly something that we will have other webinars about. Just to say perhaps that geosynthetics, one nice advantage of geosynthetics, whether they're Tensar or something else, we can use those with a wide range of fill materials. So today we talked about clays and sands and gravels, all types of different materials that we can be using as fills. And they can all be used together with geosynthetic reinforcement. Of course, we need to do some testing to find out how they interact, what the effect is, or the interaction between the geosynthetic and the fill, no problem at all. But of course, it needs testing and understanding. So I think that's rather important. Oh, it's quite a long question there. So this is something about a soil appearing, if I get this right, to have started off life as a sand, or more like a sand, and then ending up like a clay. I don't. Maybe I've got that wrong, but I need to know an awful lot more about the background of that. I think this is quite a complicated question, so let me move on from that one. But I'm happy to. We got a note of these questions, and if you want to send us emails with them, we can of course do it. Ahmed, structure design. So this is building over areas where we have high tides. I think we have tidal water, if I get it right. Yeah, when we're building fills and there's water around, we have to be very careful, of course. It's difficult to place fine fills in water, and probably it's a very good idea if you're going to use clay fills to try to avoid them, as a discussion earlier on about clay fills coming in contact with water. If you know that a fill is going to become in prolonged contact with water, then that's a good time not to be using a clay fill. So you might consider, for example, if you have an embankment where the lower part may be within the tidal range of the sea, then that lower part, it would be wise to make it a granular fill. But the upper part could still be a clay fill, no problem, because here in Indonesia, we tend to have a lot of clays, and our granular soils are often difficult to get or expensive, or they're a long way away. So we have to be a bit careful on how we do that. We have about swelling clay here, treatment by yeah, swelling clays and treatment. Of course, there are ways of treating swelling clays. Often people are doing things like mixing them with things like lime and other admixtures. But this is all to do with tunnels. I think if you're digging a tunnel through a swelling clay, I think the treatment is a bit difficult. I think that's another rather complex question, but I think the first point is being aware of it. So if you are aware that you have a swelling clay, then this is the first important step to knowing how to deal with it. So obviously, if you're digging, I mean, take London clay. London clay is a swelling clay. And there are many tunnels built through London clay, but they do all have, or they present their own particular challenges. And I think if you go into published literature, you'll find a lot of information about tunneling in London clay, which is a swelling clay. And I would recommend that's a good source of information for that kind of thing. Oh, this is a good question, actually. Another one. Ah, Sheffy is asking another question here. Distinguishing between organic soil and non-organic soil. Yeah, this is a good question. I'd have to say that people are very quick to call any organic soil peat, even if it's not peat. Now, peat, of which, I mean, Indonesia is probably, I don't know, number 3 in the world for peat deposits. I mean, Canada's the most, I think, and then Russia must have a lot. But in Indonesia, especially in Sumatra and parts of Kalimantan, we have a huge amount of peat. And peat is a very specific kind of organic soil where it is mainly organic. And in some cases, it's like the picture I showed you earlier on, which is from Sumatra, it's almost entirely organic. And there are various classification techniques for classifying organic soils because they often get mixed with mineral soil. So for example, at one end of the scale, we have pure peat. And at the other end of the scale, we're going to have a completely non-organic clay. And then you can have mixtures of the two, depending on the depositional situation. And therefore we start to get organic clays. And then we're going to get clay peats maybe, or clay organic soils. and some of these become very difficult to handle. One thing you're probably aware of is that especially peats and highly organic soils are highly compressible. But sometimes their strength is not too bad, especially their drain strength. But the clays, generally their problem is that they can be quite compressible, but then they can have very poor shear strength properties. And if you've got these interlayered, as you sometimes do, then it's a difficult combination to work with. But it's very important, though, to be clear about what you're dealing with. I'm sometimes told that, oh, we have a site where we have peat. So I'm expecting to go and see something which is almost purely organic. You get there and you find it's a clay with some organic content, but of course it smells organic. If you pick it up in your hand and smell it, yeah, you get that organic smell and you can see fibers in it. So then it would be an organic clay. And those kinds of mixed soils are quite difficult to deal with, but it is quite important to make sure that you've made that distinction. Oh, I have from Pat Trevor here. What is the best method to obtain a correlation between Atterberg limit values and undrained shear strength for preliminary design input? This is a very another good question. The only good relationship between undrained shear strength and Atterberg limit is really the remolded shear strength, because that's really the definition of the Atterberg limit values. That comes from an undrained shear strength of a remolded sample. When it comes to undisturbed soils, there isn't necessarily a very good correlation, and it'll depend on other things. So it certainly helps. I mean, we all know when we look at that profile of clay from Juru, where we have the water content up about the same as the liquid limit, we know that's likely to be a soft clay. And when we see the London clay with its water content close to the plastic limit, we know that's likely to be a stiff clay. And I think the most important thing is to get an indication of that from those diagrams where we plot water content in combination with the range of the Atterberg limits. And then you can look at that liquidity index. You will find some correlations between liquidity index and undrained shear strength, but it is for the remolded soil, not for the undisturbed soil. For the undisturbed soil, you'd have to be a bit careful, but generally they're going to be stiffer than you expect if you look at the correlations, assuming it's remolded. Remolding soils normally reduces their undrained shear strength. I think we've already been past there. Panji. How to create decision to soil maintenance with road grading in area of gravel road. I really think this is not directly a question related to this presentation, but maybe for another day. Of course, when we build gravel roads, we're very interested in the grading and the angularity of the material. So you want a well-graded material, which is angular. And in fact, that kind of material has a special name. The good old name for it is a macadam. A macadam is a naturally interlocking material that produces extremely good gravel roads. And then they had the idea of adding bitumen. So it became called a tar macadam when you allow the bitumen to kind of dribble through it. And then we got to asphalts where it's premixed. But I think looking at grading curves and angularity is going to give you a very good idea of how long gravel roads are likely to survive. And I'm afraid maintenance, you'll find out by how often it has to be maintained. But if the target is a well-graded, preferably granular material, hopefully crushed, then the life of that road can be very long. Now, just to give you some idea, in countries, particularly like Australia and New Zealand, the vast majority of roads there are gravel roads. They're often sealed with a chip seal dressing, which is very thin, but the main bearing layer, the base course, is a gravel, but of exceptionally high quality and with very, very stringent specifications. So we can build gravel roads with extremely long lifetime, but it's all down to the grading the quality of the stone material. Does it break up because gravel particles will be kind of moved around slightly by the passage of wheels. Very important to look at the gradings, angularity, hardness. These are all important features of gravels when we look at gravel roads where you want them to last for a very long time. Specific gravity, very quickly then. I need to be told by the committee, the panitia, when I need to stop looking at the questions, because I'm not quite sure about that. I think quite soon, but 5 minutes. Okay, I have 5 more minutes of questions for you. Okay, the specific gravity, the simplest way I can think about it is it's the density of the solid soil particles, except we don't quote it as a density. We quote it as a ratio to the density of water, which is around about 1 in kilograms per grams per cubic centimeter, or it's about 10 in say kilonewtons per cubic meter, and therefore it's a ratio. So, for example, if we have a specific gravity of 2.6. and we multiply that by 10, the unit weight of water, then we get 26. So you'd have a density of the solid material then of 26 kilonewtons per cubic meter, which would be very typical. Most soils, so the clay minerals, quartz, calcite, all tend to have specific gravity in the order of 2.6 to 2.7. But again, that's sometimes, you can be surprised. And sometimes you'll see soils where you get very high densities, but then you investigate and you find, it's coming from a mining area, and you've got some very heavy minerals in there because maybe it's got some contamination or some content of the material that they're trying to mine, which could be, say, a material that's going to be used to make iron or nickel or something, and then you can get very high specific gravity. So as I said before, question unusual data, but you can always expect the unexpected. So a specific gravity of 3.5 is quite possible, depending on the nature of the material, but unusual. Which type of soil will be more potential for liquefaction, alluvial or residual soil? Well, this is a good question, especially after the experience, the terrible experiences in Palu, which is what, almost 2 years ago now, a year and a half ago. Liquefaction is a horrific thing. Of course, the soils that are most susceptible to liquefaction are the relatively uniform fine sands, which tend to form a rather unstable arrangement because they're uniform, and if their particles are rather rounded, then that makes it even easier for them to collapse. But I think the experience is that there are actually also a wider range of soil types that are likely to liquefy. Generally, residual soils, unlikely. The liquefiable soils are generally much more likely to be alluvial soils, because the alluvial deposition process sorts and rounds the grains, making them into more uniform soils, the ones which are therefore much more likely to liquefy. But I'm trying to think about if we go to pure residual soils like Tanamera, that's not liquefiable, and many of the other residual soils. Generally, I can't really think of situations where they are likely to be liquefiable. I'm sure there's been some very good investigation of the soils around Palu. I went to see some of the liquefaction areas there, which was a very what I call humbling experience to see the effect of liquefaction so close up. And of course, if you want a bit more information, another place where there's a huge amount of information now is the city of Christchurch. If you look at publications about liquefaction there, you will find a vast amount of information about that. So I think the time has now come for me to bring my part of this to an end. I'd first of all like to thank everybody very much for listening in today. As mentioned before, we will have some further webinars of this time. The next one we're going to talk about, or I will talk about the shear box test and the pros and cons, the do's and don'ts, the various aspects of using the shear box test. So again, thank you all very much for listening. Thank you also very much to Multibangun Rekatama Patria for organizing this webinar, and I'll look forward to maybe seeing some of you before too long, and maybe talking to you again in the not too distant future. Thank you very much.
Oke, terima kasih kepada Pak Mike atas waktu, paparan, dan jawabannya yang diberikan. Selain itu, kami mengajak Bapak, Ibu, dan teman-teman yang hadir di sini untuk mengikuti berita dan informasi terkini seputar PT Multibangun Rekatama Patria dan MRP Webinar Series yang akan datang di bulan depan dengan follow dan like media sosial kami yang tertera pada layar Anda. Follow kami di Instagram dengan nama @multibangunrekataMapatria, Twitter kami di @multibangunrp, Facebook dan LinkedIn kami dengan nama PT Multibangun Rekatama Patria, dan kami juga hadir di TikTok dengan username Multibangun Rekatama Patria. Kepada Bapak dan Ibu, kita beralih ke sesi selanjutnya, yaitu kuis berhadiah. Kuis berhadiah ini akan dipandu oleh Mbak Rifa. Kepada Mbak Rifa, dipersilahkan.
Baik, selamat siang, selamat siang kepada Bapak, Ibu, dan rekan-rekan mahasiswa sekalian. Nama saya Rifa, saya yang akan memandu games berhadiah uang Rp150.000 untuk 3 orang pemenang yang akan kita bagikan setelah acara dengan panitia akan menghubungi para pemenang. Nah, sebelum itu akan saya share tata cara bagaimana untuk mengikuti games berhadiah ini. Sebentar. Baik, Bapak, Ibu, dan rekan-rekan mahasiswa sekalian, silahkan buka browser dari handphone atau dari laptop, jika Anda menggunakan laptop untuk membuka Zoom ini. Kemudian ketikkan menti.com. Ketika sudah mengetikkan menti.com, maka masukkan kode 9407069 dan masukkan nama Anda sesuai nama yang Anda daftarkan saat registrasi webinar ini. Atau jika lupa bisa dilihat langsung di display name di Zoom yang Anda gunakan saat ini. Sekali lagi, silahkan ketikkan menti.com. Kemudian masukkan nomor kode 9407069. Kodenya 9407069 dan isikan nama Anda sesuai yang Anda registrasikan untuk mengikuti webinar ini. Saya ketikkan juga ya di chat. Sebentar. Kodenya 9407069. Baik. Kita tunggu beberapa saat untuk agar banyak peserta yang ikut. Silakan buka browser Anda, ketikkan menti.com, masukkan kode 9407069 dan masukkan nama Anda sesuai pendaftaran. Oke. Ya, 196 peserta yang ikut. Kita tunggu sampai 200. Kodenya 9407069. Jangan lupa isikan nama sesuai registrasi agar mempermudah panitia untuk menghubungi jika nanti menang. Jadi peraturannya seperti ini. Pertanyaannya dalam bahasa Inggris dan berkaitan dengan apa yang sudah dipresentasikan oleh Pak Mike karena yang menyiapkan pertanyaan ini juga adalah Pak Michael Dobie. Pertanyaan dalam bahasa Inggris, kemudian Anda harus menjawab pertanyaan dengan benar dan cepat untuk mendapatkan bonus poin. Nanti 3 orang di akhir games dengan poin teratas atau poin terbanyak akan memenangkan masing-masing Rp150.000. Baik, masih kita tunggu. 9407069. Kita mulai 1 menit lagi ya. Ketik menti.com, masukkan kode 9407069, dan masukkan nama sesuai yang Anda registrasikan untuk masuk ke webinar ini. Kita sudah punya 225, 226, hadiahnya 150.000 loh. Jangan sampai ketinggalan. Jawab benar dan jawab cepat. Pertanyaannya hanya 3 dalam bahasa Inggris sesuai dengan yang dipresentasikan oleh Pak Michael Dobie sebelumnya. Baik, kita mulai ya. Pesertanya 228. 230. Oke, saya hitung sampai 10, kita mulai ya. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oke, kita mulai sekarang. Waktu menjawabnya 1 menit, tapi siapa yang benar, siapa yang paling cepat, dia yang mendapatkan poin terbanyak. Pertanyaan pertama. Walking on Kuta Beach near the edge of the sea, when you first put your foot down, the sand feels hard and the area around your foot becomes dry. A little later, it becomes soft. What is the main property of the sand which causes this to happen? Compaction by joggers, particle size distribution of the sand dilates when sheared, the sand is mainly quartz particles. Ayo, yang mana? Waktunya 35 detik lagi. Ya, sudah dapat jawabannya? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Kita lihat siapa yang paling tinggi poinnya di pertanyaan pertama. Oke, jawabannya berbeda-beda. Yang benar jawabannya adalah the sand dilates when sheared. Oke, kita lihat siapa yang memuncaki klasemen. Ya, untuk pertanyaan pertama dipimpin oleh James Utomo sebagai penjawab yang benar dan tercepat dengan 969 poin. Selanjutnya, pertanyaan kedua. Pertanyaan kedua. Samples of London clay and Holocene Juru marine clay are taken from 2 meters depth with phreatic surface or water table at 1 meter. Both clays have C- equal to 2 kilopascals and V- equal to 26 degrees. Undrained shear strengths are London clay 100 kilopascals and Juru clay at 8 kilopascals. What is the main reason for this difference? The clay minerals, stress history, lower water content of the London clay, or high liquidity index of the Juru clay. Waktunya 30 detik untuk menjawab. Siapa yang menjawab paling benar dan paling cepat mendapatkan poin terbanyak. Ayo, yang mana? Hadiahnya 150.000 untuk 3 orang pemenang dengan 3 poin tertinggi yang menjawab paling benar dan paling cepat di 3 pertanyaan. 3, 2, 1. Kita lihat. Yang mana jawabannya? Jawabannya adalah stress history. Untuk di pertanyaan kedua, yang memimpin klasemen saat ini adalah Pak Kustiawan dengan 1.874 poin. Menggeser Pak James Utomo yang sebelumnya di pertama. Oke, pertanyaan terakhir. Hasil poinnya akan akumulatif, jadi pemenang dengan poin terbanyak di akhir akan memenangkan. Satu lagi ya. Siap? Oke. Liquidity index for a firm clay of low sensitivity is found to be 1.3 based on Atterberg limits and water content. What is the most likely reason for this? Sample was not properly sealed and dried out. Sample was badly shaken during transport to the lab. Liquid limit measured using fall cone test. Atterberg limit samples were prepared using oven drying. Waktunya 40 detik dari sekarang. ...25 detik lagi. Silahkan dipikir-pikir. What is the most likely reason for this? Sepuluh detik lagi. Tiga, dua, satu. Waktunya habis. Jawabannya adalah Atterberg limit samples were prepared using oven drying. Oke, kita lihat siapa yang menduduki 3 peringkat teratas dan berhak mendapatkan 150.000 per masing-masing pemenang. Oh, ada yang nggak jawab ini. Selamat kepada Pak James Utomo, Davin, dan Stephen Handoko berhak mendapatkan masing-masing Rp150.000. Nanti kalau boleh di screenshot layarnya, kemudian akan menjadi bukti ketika panitia menghubungi. Sekali lagi selamat kepada Pak James Utomo, Pak Davin, dan Stephen Handoko. Segitu saja dari saya. Sekali lagi selamat kepada para pemenang. Saya kembalikan ke Mbak Astri. Terima kasih.
Baiklah, terima kasih kepada Mbak Rifa yang sudah memandu acara games berhadiah pada pagi hari ini. Dan selamat kepada pemenang. Dengan berakhirnya games tadi, maka sudah sampailah kita di penghujung acara. Untuk informasi mengenai sertifikat dapat diakses melalui link s.id/mrpweb1. Kami juga cantumkan pada kolom chat yang tertera pada layar Anda. Apabila Anda memiliki pertanyaan atau terdapat kesalahan penulisan nama pada sertifikat, silakan hubungi Mbak Rifa melalui WhatsApp yang tertera pada layar Anda di nomor 0822 9851 0700. Dan untuk informasi lebih lanjut terkait PT Multibangun Rekatama Patria dan acara-acara kami selanjutnya, silakan kunjungi kami dan ikuti kami di media sosial kami. Akhir kata, kami mengucapkan terima kasih kepada seluruh peserta, pembicara Bapak Michael Dobie, dan panitia yang terlibat dalam acara hari ini. Kami juga memohon maaf jika terdapat kesalahan dan perbuatan selama acara berlangsung. Kami menunggu Anda di MRP Webinar seri selanjutnya di bulan depan. Selamat siang dan sampai jumpa. Wassalamualaikum warahmatullahi wabarakatuh. Halo Sobat Multibangun, kali ini kita akan bahas konstruksi bangunan termegah di Indonesia. Yang pertama, segmental retaining wall system terpanjang di Indonesia. Multibox retaining wall system pada jalur kereta api Batu Ceper Tangerang ke Bandara Soekarno-Hatta. Konstruksi ini memiliki panjang 2,4 km. Yang kedua, jembatan terpanjang di Indonesia yaitu jembatan Suramadu, Surabaya Madura yang berada di Jawa Timur. Jembatan ini memiliki panjang 5,4 km. Yang ketiga adalah bendungan terluas, yaitu Bendungan Jatiluhur yang berada di Jawa Barat memiliki luas 8.300 hektar. Dan yang keempat adalah gedung tertinggi, yaitu Gedung Gama berada di Jakarta setinggi 310 meter. Dan yang terakhir adalah peninggalan sejarah termegah, yaitu Candi Borobudur. Candi ini memiliki luas 2.500 meter persegi dan tinggi 35 meter. Gimana? Menarik?
Halo Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik. Persatu, geosintetik adalah bahan tiruan atau sintetik yang digunakan dalam proyek konstruksi yang berhubungan dengan tanah atau batuan. Di video kali ini akan kita bahas adalah geogrid dan geotekstil. Geogrid adalah bahan geosintetik yang berupa lembaran dan memiliki bukaan. Ada triaxial dan uniaxial. Geogrid triaxial adalah bahan geosintetik yang memiliki bukaan berbentuk segitiga yang seperti ini. Fungsinya sebagai stabilisasi tanah dasar yang lunak pada proyek jalan dan area penumpukan. Geogrid uniaxial adalah bahan geosintetik yang memiliki bukaan memanjang satu arah yang seperti ini. Fungsinya adalah untuk perkuatan timbulan tanah atau lereng. Selanjutnya geotekstil. Geotekstil adalah bahan geosintetik berpori yang memiliki sifat tembus air. Ada woven dan non-woven. Pembahasan selanjutnya tunggu di part 2 ya. Sampai jumpa.
Halo Sobat Multibangun, kali ini kita masih akan bahas jenis-jenis geosintetik part 2. Kemarin kita sudah bahas geogrid nih. Sekarang kita bahas geotekstil. Geotekstil adalah geosintetik berpori yang memiliki sifat tembus air. Ada geotekstil woven, ada geotekstil non-woven. Geotekstil woven, geotekstil yang teranyam, terpal tuh. Fungsinya sebagai separator atau pemisah lapisan material. Selanjutnya geotekstil non-woven, geotekstil yang tidak teranyam seperti karpet. Fungsinya sebagai penyaring lapisan material tanah. Gimana? Udah tahu kan tentang geotekstil? Part selanjutnya kita akan bahas geomembran. Ditunggu ya.
Halo Sobat Multibangun, di video kali ini kita akan bahas jenis-jenis geosintetik part 3. Di video sebelumnya kita udah bahas tentang geotekstil. Nah, di video kali ini kita akan bahas tentang geomembran. Geomembran adalah geosintetik yang memiliki sifat kedap atau tidak tembus cairan. Fungsinya adalah mencegah cairan masuk ke dalam tanah atau menembus material tertentu. Geomembran biasanya digunakan untuk embung atau kolam penampungan air, kolam limbah, tambak udang, dan tempat pembuangan sampah akhir atau TPA. Sekarang udah pada tahu kan tentang geomembran? Tunggu video-video kita selanjutnya ya. Hei, pada serius amat. Gombalan teknik sipil cek. Mas Andi, gombalin dong.
Kamu punya teodolit nggak?
Buat apaan?
Karena aku mau mengeker atau melihat perasaanmu padaku.
Mbak Astri, gombalin juga dong.
Sekokoh-kokohnya pondasi tiang pancang, lebih kokoh cintaku padamu.
Mas Bagus, gombalin juga dong.
Kamu lulusan teknik sipil ya?
Kok tahu?
Iya, karena kamu berhasil membuat jembatan hati antara aku dan kamu.
Mbak Wira juga dong.
Berbulan-bulan di proyek, aku sanggup. Gimana kalau cuma menunggu kepastian kamu?
Patri, gombalin dong.
Jalan dan gedung aja aku bangun, apalagi membangun rumah tangga dengan kamu.
Pak Jamal, ayo.
Aku nggak biasa ngebalik.
Ya, Pak Mamo deh.
Aku udah terbukti.
Halo Sobat Multibangun, di video kali ini kita akan bahas istilah-istilah pada konstruksi flyover. Flyover atau jembatan layang adalah jalan yang dibangun di atas kawasan atau jalan atau jalur kereta api atau persimpangan jalan untuk menghindari kemacetan lalu lintas. Nah, ini nih bagian-bagian dari konstruksi flyover. Nah, yang ini namanya abutment, fungsinya untuk menopang jembatan di bagian ujung-ujung jembatan. Oprit jembatan atau jembatan pendekat adalah timbunan tanah atau urukan di belakang abutment. Ini girder, struktur horizontal yang menopang bagian utama jembatan. Ini adalah pier, struktur vertikal yang menopang girder jembatan. Ini dinding penahan tanah, yaitu dinding penahan timbunan tanah di bagian oprit flyover. Tiang pancang atau bore pile adalah struktur di dalam tanah yang menahan jembatan.
Halo Sobat Multibangun, video kali ini kita akan membahas perbedaan antara insinyur sipil dan insinyur arsitek. Insinyur sipil menghitung kekuatan bangunan. Insinyur arsitek mendesain keindahan bangunan. Insinyur sipil mendesain sarana dan prasarana seperti jalanan dan jembatan. Insinyur arsitek mendesain tata kota. Insinyur sipil harus mahir menghitung. Insinyur arsitek harus mahir seni menggambar. Insinyur sipil tidak harus paham warna. Insinyur arsitek harus paham warna. Kalau insinyur sipil bisa jadi konsultan atau kontraktor. Insinyur arsitek biasanya jadi konsultan perencana. Bagaimana? Udah tahu kan perbedaan antara insinyur sipil sama insinyur arsitek? Sampai jumpa!
Halo Sobat Multibangun, di video kali ini kita akan membahas alat pelindung diri yang ada di proyek. Yang pertama, helm proyek. Kayak video yang kemarin jangan lupa dicek ya. Fungsinya untuk melindungi kepala kita dari benda yang jatuh dari atas. Walaupun ini jangan digunakan untuk naik motor ya, karena itu nggak aman. Yang kedua, safety shoes. Fungsinya sebagai pengaman pada tempat berlumpur atau becek. Juga mencegah kecelakaan fatal pada kaki. Selanjutnya, rompi proyek. Ia memiliki material retroreflektif agar mudah terlihat di lokasi proyek, terutama di malam hari. Berikutnya, sarung tangan. Fungsinya untuk melindungi tangan dari kecelakaan kerja seperti terpotong, tertusuk, dan terjepit. Selanjutnya, kacamata safety. Fungsinya melindungi mata dari debu dan partikel-partikel kecil yang berbahaya. Dan yang terakhir, body harness, biar tidak terjatuh. Nah, jangan lupa pakai APD ya.
Halo Sobat Multibangun, udah pada tahu belum? Ada dua jenis pekerjaan teknik sipil, konsultan dan kontraktor. Cari tahu yuk perbedaannya. Konsultan kerjanya menghitung dan mendesain proyek serta mengawasi proyek. Kalau kontraktor melaksanakan proyek sesuai desain dari konsultan. Konsultan bisa kerja sendiri. Kalau kontraktor pasti harus bersama tim. Konsultan bekerja di kantor, tapi konsultan pengawas bekerja di lokasi proyek. Kalau kontraktor pada umumnya bekerja selalu di lokasi proyek. Nah, sekarang udah tahu kan bedanya antara konsultan dan kontraktor? Sampai jumpa lagi! Halo Sobat Multibangun, kali ini kita akan bahas jenis-jenis alat berat yang digunakan di proyek. Yang pertama namanya ekskavator atau disebut juga backhoe. Fungsinya untuk menggali dan memindahkan material seperti tanah dan batu. Yang ini nih namanya dozer. Fungsinya untuk mendorong material tanah ke depan atau ke samping. Kalau yang ini nih namanya kompaktor. Fungsinya untuk memadatkan tanah atau timbunan. Nah, yang ini nih namanya dump truck. Fungsinya untuk mengangkut dan memindahkan material seperti tanah, batu, besi, dan lain sebagainya. Yang ini namanya grader. Fungsinya untuk meratakan tanah atau material. Gimana? Sekarang udah paham kan jenis-jenis alat berat yang dipakai di proyek? Sampai jumpa!
Halo Sobat Multibangun! Masih ngomongin multi-group rating wall system nih. Jadi ceritanya PT Kereta Api Indonesia akan membangun jalur kereta api dari Bandara Soekarno-Hatta sampai ke Batu Ceper, Kota Tangerang. Tantangannya adalah, pertama, jalur kereta ini melalui pemukiman yang padat penduduk. Dan yang kedua, harus lebih tinggi dari lokasi pemukiman. Maka multi-group retaining wall system adalah solusi yang tepat untuk tantangan itu. Karena multi-blok tidak memerlukan banyak alat berat yang bisa merusak dan mengganggu pemukiman penduduk di sekitar proyek. Dan satu lagi, Permukaan multiblok bisa dibuat lebih keren dengan mural. Gimana? Menarik kan? Halo Sobat Multibangun. Perhatiin deh, kenapa kalau di proyek warna helm kok beda-beda ya? Ada yang warna kuning, ada yang warna biru, ada yang warna merah, warna putih. Yuk kita bahas. Helm proyek warna kuning dipakai oleh pekerja umum dan subkontraktor seperti ini. Helm proyek warna biru dipakai oleh pekerja dengan posisi sebagai set supervisor kelistrikan dan operator teknis seperti ini. Helm proyek warna merah biasanya dipakai oleh petugas keselamatan dan kesehatan kerja seperti ini. Selanjutnya, helm warna putih nih. Biasanya dipakai oleh manajer, pengawas, insinyur, dan mandor deh. Gimana? Udah jelas kan Sobat Multibangun? Bye! Halo Sobat Multibangun!
Tahu nggak sih apa itu dinding penahan tanah atau retaining wall? Dinding penahan tanah atau retaining wall adalah struktur bangunan penahan timbunan tanah. Begini nih contohnya. Ada yang terbuat dari batu kali, terbuat dari beton dicor, terbuat dari beton dipancang, dan yang ini dari multiblok. Multiblok retaining wall system adalah dinding penahan tanah yang merupakan kombinasi dari blok beton dan tensar RE geogrid. Begini nih gambarnya. Di bagian dalam multiblok retaining wall system ada tensar RE geogrid yang ini nih, yang fungsinya untuk menahan tanah. Di depannya ada blok beton. Ini. Fungsinya sebagai penutup muka dinding. Gimana? Udah ngerti kan?